Welcome back to The Deep Dive, the show engineered to give you the ultimate shortcut to being truly well-informed.
Oh,
Today, we are strapping in for a deep dive not just into the future of transportation, but into the structural transformation of massive national infrastructure. We're going to be focusing specifically on the railway system in Great Britain.
yeah, this is the topic that really elevates artificial intelligence from just a concept to a fundamental operational necessity.
Yeah.
We're looking at an industry report that details how AI isn't just optimizing trains. It's becoming the central nervous system for what is, one of the most historically complex and densely operated rail networks in the world.
Exactly. Our source material today is a recent and pretty influential industry analysis. It details how AI integration is set to transform the UK's rail network into what the authors are predicting will be a global blueprint for efficiency. So the mission today is precise. We are extracting the most vital insights regarding this AI integration, focusing specifically on the sheer staggering scale of predicted growth and the sophisticated new roles AI has to adopt to manage it.
And to put a timestamp on this, the report projects major systemic change by the mid-2030s. So we're not talking science fiction here.
Not at all.
This isn't just about small tweaks. It's a total shift, with the entire system driven by advanced digital platforms and, of course, AI. It's essentially a roadmap for handling a complexity crisis that is facing nearly every major global metropolitan area.
And here is the core challenge that anchors this deep dive for you, the listener. How, precisely, is AI poised to handle an influx of an additional billion journeys?
An additional billion. It's an incredible number.
On this already congested system, we're talking about scaling capacity by a massive percentage in just over a decade, using infrastructure that, in many places, is over a century old.
Yeah.
Okay, let's unpack this enormous challenge.
Let's do it.
So, the numbers are really the starting gun for this entire conversation, aren't they? They define the mountain we have to climb.
Absolutely.
Let's establish the baseline. The report says 1.6 billion passenger trips were recorded in the UK just in the year leading up to March 2024. That's today.
Right. That's our starting point. 1.6 billion and the future projection.
Right.
By the mid-2030s, this network, which is already one of the busiest per mile anywhere in the world, is projected to accommodate an extra billion journeys annually.
An extra billion.
That's the key figure. We're moving from 1.6 billion trips toward 2.6 billion or, potentially even more in a very short time frame. This isn't that sort of gradual, steady growth we saw in the mid-20th century.
No.
This is a step change, a massive increase in density and required capacity.
When you look at that spike, going from 1.6 to 2.6 billion, that's roughly a 60% uplift in passenger demand. It makes you wonder, are these reports being a little bit optimistic? Can the existing infrastructure actually absorb that kind of load, even with new digital systems?
That's the million-dollar question, isn't it? And the report argues that the infrastructure can handle the increased physical load, but, and this is the big but, only if its utilization is completely radically optimized.
Okay.
This magnitude of growth means the network will inevitably transform into what the report describes as a bustling hub of complexity.
I like that phrase.
It's not just about buying more trains. It's a challenge of resource allocation, of pathing, of maximizing the use of every available minute on the track and at the platform edge. The only way to survive that kind of density is through near-perfect efficiency.
Right. Let's focus on that near-perfect efficiency.
Right.
Why can't traditional systems, the manual ones or even the legacy computerized controls, why can't they simply be scaled up to manage this 60% uplift? They've managed railways for generations.
Because traditional linear systems hit what we call the complexity ceiling.
The complexity ceiling.
Exactly. They operate on fixed timetables, and they rely on human dispatchers or, older algorithms to follow a defined schedule. And they are fantastic when everything is working perfectly.
Which it never is.
Which it never is. Railway operations are inherently nonlinear and, frankly, chaotic. The moment one disruption occurs, a signal failure, a late-running freight train, severe weather, the system instantly flips into chaos mode.
So the problem isn't handling the normal state. It's handling the inevitable abnormal state, but now multiplied by this huge increase in volume.
Precisely. In the normal state, the 1.6 billion journeys are tough, but they're manageable. Add the extra billion, and suddenly the frequency of interaction and the conflict points, they scale exponentially. It's not a linear increase.
Right.
A small 5-minute delay caused by, say, a track circuit issue doesn't just affect the trains immediately behind it. It sets off a chain reaction. It forces a decision on whether to hold a high-speed train, which delays the ability to move an empty stock train recorded for the evening peak, and that throws off the mandated rest break timing for 3 different driver crews.
And a human controller or even a legacy computer that handles things one by one sequentially, they just physically cannot analyze those 10,000 potential cascading effects, right?
Not in real time.
They can't calculate the best scenario to minimize the total delay across the whole network and then implement all the necessary changes instantly.
They're too slow, and their analytical scope is too limited. So what happens is they end up defaulting to safe but very suboptimal recovery strategies.
Which usually means massive system-wide delays for everyone.
Exactly. The sheer computational volume, dictated by managing 2.6 billion plus movements, demands a technological transformation. The future railway has to be characterized by advanced digital systems and, most critically, interconnected control that can instantly process this level of chaotic complexity.
So AI isn't an option here. It's not a nice to have.
It's the only mechanism capable of breaking through that complexity ceiling. It's what transforms a challenge from being operational to being fundamentally computational.
Okay, so if we look at this from the perspective of avoiding systemic failure, which is what happens when that complexity just overwhelms the human element, then this shift to AI becomes an absolute necessity.
It does.
It's not just a modernization project. It's the difference between merely coping with demand and actually strategically optimizing every single available asset you have.
And the capacity of AI to manage this nonlinear complexity hinges entirely on the quality and the structure of the underlying digital ecosystem.
Mm-hmm.
The report clearly defines the 3 foundational elements, what we call the transformation triangle, that have to be fully established before AI can perform its most advanced functions.
So if AI is the sophisticated brain, we need to talk about the sensory organs and the nervous system first.
That's a great analogy.
What is the first pillar of this foundational architecture?
The first pillar is advanced digital systems. These are the essential replacements for the legacy signaling and control technology. This is where we move away from physical, trackside signaling, the colored lights that tell the driver what to do.
The classic traffic lights for trains?
Exactly. And we move towards cab-based signaling, specifically systems like the European Train Control System, or ETCS, or other similar digital overlays.
Can you elaborate on the difference there? Why is cab-based digital signaling such a game changer for AI?
Yeah, of course. So in the old system, signals are physical assets installed every few kilometers on the track, and they regulate traffic flow in fixed, predetermined blocks.
Okay.
The safety system relies on a physical mechanism to prevent 2 trains from being in the same block. But this creates physical speed constraints and operational bottlenecks because the blocks are all fixed sizes.
And the digital system, how does that work?
The digital system, like ETCS level 2 or 3, uses radio communication GSMR to send real-time movement authorities directly to the train's cab.
So it's right in front of the driver.
Right in front of the driver.
Yeah.
And this allows for what is called moving block signaling. Instead of fixed blocks on the ground, the safe distance between 2 trains is calculated dynamically in real time based on their speed and their braking profile.
Ah, so it's a virtual safety bubble that moves with the train?
Perfectly put. It's a virtual safety bubble. And this dynamic calculation instantly increases track capacity, potentially by 30 to 40% in dense areas, just because trains can safely run closer together.
Wow.
And crucially, it provides the essential platform for precise, comprehensive, real-time data collection and automated intervention that the AI absolutely needs.
So the switch to digital systems removes the physical constraints of legacy tech and provides a sort of standardized digital language for the whole network to speak.
Yeah.
That sounds like a monumental multi-decade upgrade project in itself, though.
It is, and its success hinges entirely on the second pillar, a wealth of data.
Right.
AI algorithms are, they're useless without extensive, high-quality, and fast-flowing data. When we say wealth of data in this context, we're not talking about aggregated monthly reports. We're talking about granular, high-volume sensor readings flowing constantly.
Let's dig into that data granularity. What are the specific inputs that are feeding this central AI? What is it actually looking at?
We need to move beyond simple telematics, beyond just train X is at location Y. The AI is consuming data from literally thousands of points. Trackside sensors, monitoring rail temperature, vibration, and gauge width every single second. detailed operational diagnostics from every single component of the trains themselves, measuring friction, individual axle performance, even oil quality.
And passenger flow, you mentioned that. How granular does that actually get?
Think about it like this. Knowing not just how many people boarded the train at the first station, but tracking occupancy levels car by car in real time,
Okay.
and even anticipating exactly where passengers will get off based on historical patterns and maybe even real-time destination changes from ticket apps.
So the system could predict not just delays, but also a potential crowding risk on a specific platform at a specific station 10 minutes from now.
Exactly. This data has to be constantly streaming high velocity and clean because the AI needs to make decisions instantaneously. Without this wealth of data, the AI is effectively operating in the dark. It's unable to model the complexity accurately.
That truly paints a picture of a digital twin, a complete, constantly updated living simulation of the entire railway system.
It's the goal.
But that requires a phenomenal level of coordination, which I guess brings us to the third foundational element, a network of interconnected suppliers.
And this is often the biggest non-technical hurdle. It's crucial to understand that no single company built this railway or provides all the technology.
Right.
You have different entities providing the trains, different ones managing the tracks, separate companies installing the signaling systems, and still others actually running the trains.
Okay, wait. Is the report being a bit naive about the commercial friction here? I mean, if Company A makes the axles and Company B makes the scheduling software, and they're both commercial entities, how do you force them to share competitive data? Sometimes that includes trade secrets about component performance or maintenance costs. How do you get them to feed that into a centralized, transparent AI hub?
That is the ultimate challenge the report addresses. The blueprint isn't just technical. It has to be regulatory and commercial. Success hinges on establishing mandatory, standardized data protocols and a framework that overrides those competitive instincts.
So the government or a regulator has to act as the central enforcer.
Essentially, yes, they have to enforce a common data architecture, a unified data lake, if you will, where specific, maybe anonymized operational performance data is considered a shared asset that's necessary for system resilience.
So the health data from a Siemens-built train axle is immediately and automatically routed to the Alstom-built signal system and ultimately fed to the central AI system, regardless of who owns the data.
Exactly. The report implies that this level of interoperability, where all systems feed standardized, trusted data into that central AI intelligence layer, is non-negotiable for managing the expected density. If any one of those three pillars fails, the entire system just reverts back to its current complexity ceiling.
And that makes the extra billion journeys impossible to manage efficiently.
Impossible.
So the synergy is the real unlock here. Advanced digital systems provide the structure, the wealth of data provides the raw, continuous intelligence, and the interconnected suppliers ensure the data flows freely and reliably. It's the ecosystem that allows the AI to finally work its magic and begin the process of dynamic management.
Well said.
Okay, here's where we transition from the necessary foundation to the revolutionary capability. This is, for me, the core aha moment of this deep dive. The report is very clear on this. AI in rail is moving decisively beyond mere predictive maintenance.
This is the fundamental conceptual shift. Predictive maintenance is valuable, don't get me wrong, but it's narrow. It's about anticipating a specific mechanical failure. The new paradigm is systemic anticipation, moving from preventing a broken part to preventing a broken system.
Okay, let's define the traditional way first. Traditional predictive maintenance is component level. It's a sensor telling us a gearbox temperature is spiking, which means it has, say, a 70% probability of failing in the next 2 weeks.
Right. So we intervene, we replace it, that saves money and prevents a major delay. Simple.
But the new AI paradigm, it uses that massive data foundation we just talked about to watch, learn, and predict various scenarios across the entire interconnected network.
It's holistic optimization and risk modeling. The AI is less concerned with if a single part will fail and more concerned with what the system should do if three totally unrelated events, a minor signal fault, a sudden weather change, and a passenger medical emergency, all happen at the same time.
That changes the operational mandate entirely. Let's break down those three concepts, starting with watching. How does continuous context-aware monitoring across a network of this scale fundamentally differ from the old monitoring system?
Well, old monitoring was often siloed. You had track data over here and train data over there.
Right.
Watching in the AI context means data fusion and context awareness. The AI isn't just logging a temperature reading, it's correlating a specific piece of data with every other relevant input it has.
Okay, give me an example.
For instance, the system observes a train is running 3 miles per hour below its mandated speed on a particular curve. It then fuses that, marginal deviation with the fact that trackside acoustic sensors detected a slight flat spot on that train's wheel 4 hours ago, and the current weather data shows a strong headwind.
So it's integrating physics, maintenance history, and the external environment all at once.
All at once. It doesn't just look for a big red flag. It looks for thousands of subtle, interconnected data points that, when you combine them, indicate a developing systemic risk. It might determine that the suboptimal speed is being caused by an early sign of friction failure on the wheel combined with the headwind, and that if this train continues on its current path, it will cause 15 minutes of delays by the next junction.
Demanding immediate speed regulation or pathing adjustments to prevent that?
Precisely. This integrated watchfulness prevents small, initially unnoticed deviations from growing into network-crippling problems.
This moves us into the second part, learning. How does an AI develop a dynamically adaptive model of optimal performance over time? And I guess, how does it avoid simply replicating human biases or past inefficiencies?
That's a great question. Learning is where the AI proves its value over just static programming. It synthesizes current data with years of historical performance and uses methods similar to reinforcement learning.
Okay.
Optimal performance isn't just about hitting a polished timetable. It's about achieving that schedule while minimizing energy draw, mechanical wear, and maximizing passenger satisfaction, all at once.
So if human controllers historically routed all trains through Junction A during the 9 a.m. peak, but the AI, through simulation and learning from live data, discovers that routing just 10% of those trains through a slightly longer but less congested Junction B saves, 1,000 passenger minutes of total delay.
Then the system incorporates that as the new optimum.
Exactly.
It constantly A/B tests operational strategies in a simulated environment derived from that digital twin. It learns that optimal on a Tuesday afternoon during a heat wave is vastly different from optimal on a cold Saturday morning.
It's adapting its own definition of what's good.
Yes, based on live constraints, energy prices, crew availability, component health. It refined its own efficiency parameters based on evidence, not just adherence to rigid, pre-programmed rules.
And that learning capability is what enables the truly revolutionary function, predicting various scenarios. Let's spend some time here because this is what breaks that complexity ceiling we talked about.
Absolutely.
Give us a detailed breakdown of the mechanics behind predicting that cascade effect.
Okay, so this relies heavily on some advanced computational techniques, like graph theory and probabilistic modeling. Imagine the railway network as a massive graph. Every junction, every track segment, every platform, every train is a node or an edge on that graph. When a 5-minute delay is confirmed on line A, the AI instantly runs simulations across that entire graph. It doesn't just look at the next train on line A. It calculates, based on real-time crew schedules, train paths, and platform allocations, that the delayed train will now occupy platform 4 at the main terminal 5 minutes later than planned.
And what happens because Platform 4 is occupied for those extra 5 minutes?
The AI knows that Platform 4 was required by the 10.45 commuter service. That commuter service now needs a new platform or it faces a delay itself. Finding a new platform might involve rerouting it across a busy junction, which in turn impacts 3 other fast trains. At the same time, the crew assigned to the delayed Line A train was supposed to sign on to a new service on Line B 10 minutes after their original arrival time.
So now they might miss their connection.
The AI models the probability of that crew making the sign-on. It finds that the probability is low, which triggers a potential crew resourcing crisis for Line B in about an hour's time.
So a simple 5-minute physical delay immediately translates into a calculation of lost crew time, blocked physical assets, and increased conflict probability at multiple junctions down the line.
Yes, and the AI synthesizes all these cascading probabilities, crew, asset, path, to determine that the total cumulative cost of the network is not 5 minutes, but 45 minutes of distributed delay across dozens of future services.
Wow.
And knowing this allows operators to take drastic preemptive action. They could instantly cancel a minor service or reposition a spare crew to nip the problem in the bud before it spreads. This is the definition of breaking the complexity ceiling.
That's phenomenal. It turns a reactive operational team into an entirely proactive one. Now let's look at the second advanced prediction capability, optimal routing changes based on unexpected events.
This is critical for resilience. In the old system, a track issue meant a line closure and, simple diversions or just indefinite stops.
Right, wait here for further instructions.
Exactly. Now, if a track defect is detected, the AI instantly models the best alternative paths for every single train affected over the next several hours. And it's not just finding an alternative route, it's calculating the least disruptive route for the system as a whole.
How does it weigh the competing factors, like passenger convenience versus operational cost?
It uses weighted metrics. For example, the AI might calculate that rerouting a high-speed intercity train carrying 500 people onto a slower relief line only adds 10 minutes to their journey. But by doing so, it allows 4 separate commuter trains carrying a total of 2,000 people to stay perfectly on schedule.
So the total passenger benefit outweighs the individual inconvenience.
Precisely. It prioritizes overall system velocity and capacity utilization. And this complex modeling happens in seconds, providing human operators with, say, 3 optimal pre-calculated options, complete with predicted outcomes for total system delay for each one.
And the third major predictive scenario, the dynamic energy management we touched on earlier.
Right. The AI predicts the precise required energy input for a specific train based on its current load, the track gradient, and climate conditions, and it does this moment by moment.
So if you have a fully loaded freight train going up a steep hill,
A 2% gradient, say. The AI calculates the minimum required power to maintain schedule without any wasted effort. But crucially, it also manages the descent and the approach to stations. It understands where energy can be maximized via regenerative braking.
so it's managing the throttle and the braking as a function of minimizing total energy consumption while still hitting the timetable.
Exactly. It forecasts when a train needs to start its coast-to-stop maneuver, when the driver should effectively let off the power and allow the train's own momentum to carry it toward the stopping point.
Which minimizes braking, maximizes that kinetic energy recapture, and ensures a smooth arrival.
Yes. And this dynamic moment-to-moment energy forecasting translates to multi-million-pound annual savings and a massive environmental benefit. The result of this whole shift is clear. The focus is dramatically moved to enhancing overall efficiency, capacity, and safety through dynamic network-wide optimization. It makes the entire system adaptive rather than rigid.
Now we can translate the conceptual power of watching, learning, and predicting into tangible, practical benefits. The things that impact everyone, from the dispatchers in the control room to the passenger waiting on the platform.
Right. This is where the rubber meets the road, or I guess the wheel meets the rail.
Let's analyze the first pillar of improvement, one, optimizing routes. This goes beyond just the predictive conflict resolution we discussed. What does operational optimization look like in practice when you're managing a density of 2.6 billion movements?
It means the AI is functioning as an electronic air traffic control system, but for ground transport. It's dealing with minute-by-minute adjustments to the operational schedule. Optimization really means managing the interaction between different classes of trains.
You mean slow, heavy freight trains sharing track with medium-speed regional services and high-speed intercity services all at the same time?
That's the constant juggling act, exactly. Freight trains require longer braking distances, and they tend to use paths that could otherwise be optimized for faster passenger trains.
So that's the tension the AI resolves.
It is. It uses the digital signaling to tighten the headways, the distance between trains safely. But more importantly, it manages holding times. The AI might decide that holding a slow freight train on a siding for exactly 5 minutes and 30 seconds is the optimal strategy.
Why that specific time?
Because that specific window allows 4 passenger services to pass without having to reduce their speed at all. Previously, a human might hold that freight train for a safer but suboptimal 15 minutes, just to be sure.
I see.
The AI minimizes the cost of waiting time across the entire system.
Can the AI differentiate its strategy based on the type of rolling stock? A brand new high-speed train needs a different optimization profile than, say, an ancient commuter train, right?
Absolutely. The AI incorporates the specific performance characteristics of every single vehicle: its acceleration, its braking curves, its maximum speed, energy profile, even the current wear levels on its components.
So it's not a one-size-fits-all approach.
Not at all. When optimizing a path, it's not applying a generic rule. It knows that high-speed train A can accelerate to 125 miles per hour in 90 seconds, whereas regional train B takes 140 seconds. This hyper-specific knowledge allows for incredibly tight pathing without sacrificing safety, squeezing out capacity that manual systems simply could not access.
Okay, the second pillar, too, managing energy consumption. We know it's achieved through that optimal acceleration and deceleration, but let's just quantify the significance of this energy saving for you, the listener. How does this translate to economic and environmental change?
The change is transformative on two fronts. Economically, energy is one of the highest variable operating costs for any railway. By implementing those coast-to-stop profiles and maximizing regenerative braking.
Where the energy normally lost during braking is fed back into the traction network.
Exactly. The AI is directly cutting operational expenditure. We are talking about potential double-digit percentage savings in electrical energy consumption across the entire network.
And environmentally?
Environmentally, it's all about reducing the carbon footprint per passenger kilometer. Since the AI minimizes wasted power avoiding unnecessary acceleration or sharp braking, it makes what is already the most sustainable mode of transport even more sustainable.
And that's a massive selling point when national governments are committed to decarbonization targets.
It is. Rail becomes the undisputed leader in sustainable mass movement, and it's backed by real-time data on reduced energy draw.
And finally, the third and most direct impact on the end user. 3, improving the overall passenger experience. When we talk about handling an extra billion journeys, we need passengers to actually trust the system.
And reliability is paramount. By proactively resolving conflicts and avoiding those cascading delays that plague current operations, the AI guarantees that trains run on time more frequently. The confidence that the published schedule is the reality of the service. That is the bedrock of passenger satisfaction in mass transit.
But what about the moments when things do go wrong? Because they still will. How does AI improve the experience then?
It improves communication and station flow management. When a disruption is inevitable, the AI's scenario prediction capability allows for delay forecasts that are far more accurate than current human estimates.
So no more a delay of approximately 5 minutes that turns into 30.
Hopefully not. If the AI determines that a 10-minute signal failure will lead to a 25-minute system-wide delay, that is the information immediately provided to you, the passenger, rather than a hopeful guess. Trustworthy, accurate information manages expectations and reduces frustration dramatically.
And the flow management. Say there's a major sporting event or a weather disruption.
Okay, so the AI, watching the real-time passenger flow data, can predict that 5,000 people are about to arrive at a small suburban station because of an unexpected connection from a delayed express train.
A potential safety issue.
A huge one. So it can instantly communicate with station staff, automatically update digital signage to guide crowds, or even direct subsequent trains to bypass that station temporarily to alleviate the dangerous crowding risk. It allows for proactive, immediate safety and flow management that drastically improves the chaotic reality of a system operating close to its capacity limits.
So the cumulative effect is a system that isn't just technologically advanced, but fundamentally quieter, more predictable, and less stressful for the massive volume of travelers it needs to accommodate.
Reliability is the silent benefit delivered by all that complex data modeling.
The final expansive message of the report is that the UK's integration of AI in rail presents a blueprint for global railway systems. This moves the conversation beyond just national borders.
It does.
Why is the UK, with its legacy infrastructure and famously complex network, the ideal model for the world? Why not a brand new high-speed rail line in, a sparsely populated region?
Because the UK system is highly mature, it's highly constrained geographically, and it's historically complex. It has to integrate centuries-old tunnels and bridges with cutting-edge digital signaling, all while managing enormous passenger density. If AI can solve the capacity and complexity problems in this bustling hub of complexity, a system built layer upon layer over 180 years, it proves the technology is robust enough for any mature, overburdened network anywhere in the world.
So the solution is exportable precisely because the problem it solved was so difficult and so constrained.
Exactly.
That makes it instantly relevant to, say, the densely packed regional networks of Japan, or the aging Northeast Corridor in the US, or the rapidly expanding yet capacity-constrained urban networks across Europe.
All of them. And the most compelling reason for global relevance is the overwhelming trend of urbanization demands. The world is shifting into megacities, Efficient mass transit isn't a civic nicety anymore, it's an economic necessity. Cities cannot grow or maintain productivity if their transportation arteries are constantly choked.
And since railways often form the primary spine of mass transit, that 60% uplift in demand challenge the UK faces is mirrored globally in any growing metropolitan area.
Just think about the capacity crisis in places like Mumbai or São Paulo, or even the commuter rings around Paris and Berlin.
Right.
They are all grappling with how to increase passenger throughput without spending tens of billions on entirely new track construction, which is often politically impossible and environmentally disruptive.
So AI-driven systems offer a capital-efficient alternative. They unlock capacity within the assets you already have.
They are the essential ingredient for handling increasing passenger capacity when infrastructure expansion just isn't feasible.
Beyond capacity and population shifts, there is the powerful intersection with the sustainability imperative. We talked about operational efficiency, but how does AI strengthen rail's position in the global fight against climate change?
It solidifies rail's position as the greenest option. Full stop. Every minute of optimization, every use of those coast-to-stop profiles, every maximized instance of regenerative braking, it all compounds. The AI transforms rail operations from being merely sustainable into being actively hyper-efficient.
So the argument is simple. If we can make rail more reliable, more efficient, and demonstrably lower in energy consumption per passenger mile, we accelerate the necessary modal shift.
Exactly. People and businesses will choose the smart, efficient railway over less efficient road freight or air travel for short-haul journeys.
The report positions this AI-driven network not just as an operational success, but as a global standard bearer, leading the way in technological innovation while simultaneously making huge strides toward vital climate goals.
The vision is for infrastructure growth and environmental stewardship to become two sides of the same AI-driven coin.
The overall concluding vision, then, is that AI creates a railway system that does more than just cope with the future capacity crisis of that additional billion journeys. It provides a replicable, high-density, low-carbon model for how the world handles its most intense urbanization pressures and infrastructure challenges.
We covered an incredible amount of complexity in this deep dive, moving from specific UK capacity metrics all the way to the global necessity of optimized infrastructure.
Let's quickly recap the core insights for you, the learner. We established the overwhelming scale of the predicted growth, the challenge of managing an additional billion trips by the mid-2030s, and why that necessitates breaking the traditional complexity ceiling.
Second, we detailed the three foundational pillars, those advanced digital systems like moving block signaling, the wealth of data with its granular real-time sensor fusion, and the challenging necessity of interconnected suppliers that form the essential ecosystem for AI to function.
And most critically, we define the conceptual shift in how AI is being used, the move beyond basic predictive maintenance to dynamic scenario prediction, enabling the system to actively watch, learn, and predict various scenarios.
Right, like modeling the exact 45-minute cumulative delay that results from a minor 5-minute fault.
And finally, we saw the tangible impact of these advancements in concrete applications. Hyper-optimization of routes across mixed traffic, massive savings and sustainability gains through dynamic energy management, and a fundamentally better, more reliable passenger experience. So what does this all mean for you? This knowledge is your shortcut to understanding how AI is being strategically deployed, not in a shiny new sector, but to fundamentally solve the most intractable capacity and complexity problems in established, vital physical infrastructure worldwide.
It's about making the old world ready for its future.
And that leads us to the final provocative thought we want to leave you with, building on this idea of a global blueprint.
If AI can successfully manage the complexity of interconnected railway systems, which involve highly constrained physical movement, massive safety regulations, and commercial friction, what other massive established global infrastructures are next in line for this level of AI-driven watching, learning, and predicting?
That's a great question. You think about critical global supply chains where every container movement is a node on a graph, or interconnected national energy grids dealing with variable renewable inputs from solar and wind.
Or even the complex municipal water distribution networks that are servicing these massive populations. The blueprint for dynamic complexity management perfected on the tracks of the railway might just be the blueprint for managing the future of all our core global systems.
So the tracks are laid, the new system is learning.
And the future of complex infrastructure is watching.
We hope this deep dive has given you plenty to think about. Thank you for tuning in.
Safe travels.